Chinese scientists have created a super-fast analog chip and artificial intelligence. According to researchers from Peking University, the device could work 1,000 times faster than top digital processors.
A single chip, the size of your palm, made from an exotic material called lithium niobate, capable of outrunning the world's most powerful data processors by 1,000 times the speed. The numbers don't lie. We're talking about a leap that goes far beyond the boundaries of regular evolution, challenging the very laws of electrical computing physics as we know them. In the heart of the global AI race, everyone was focused on the frantic competition between companies like NVIDIA, churning out bigger, more power-hungry GPU units. But suddenly, an unexpected Chinese breakthrough emerges from Peking University in collaboration with ChipX and Turing Quantum. They unveiled the hidden giant, a photonic quantum chip designed for industrial use, operating with light instead of electricity. This invention isn't just some prototype, it's a system already deployed in critical sectors, from complex aerospace simulations and ultra-fast financial analysis all the way to molecular modeling in biomedicine. This isn't a story about the future, it's about the present that begins now. To keep up with this revolution, hit that like button, share your thoughts on light technology in the comments, and subscribe to the channel to get the secrets of scientific advancement first. To grasp the magnitude of this achievement, we need to look at the modern computing dilemma, power and heat. We've reached a critical point where companies expect to spend more on electricity bills than they do on purchasing the hardware itself. AI systems demand enormous amounts of power just to train large language models. The reason lies with electrons. When electrical currents pass through the microscopic circuits in a GPU, they generate massive thermal resistance. This resistance requires huge cooling systems, which now form the biggest bottleneck in modern data centers, consuming space, money, and effort. Chinese researchers have offered a radical solution, a transition from electronics to photonics, using light and photons instead of electricity. Photons, unlike electrons, generate virtually no heat as they travel through optical pathways. This directly solves the cooling problem and opens the door to data transfer speeds that are simply impossible to achieve with traditional electrical circuits. So what exactly makes this chip so special? We're not talking about a massive traditional quantum device that requires extreme cooling conditions like liquid cooling near absolute zero. Instead, this is a small, intricate piece of engineering. The core technology, lithium niobate. The foundation rests on a 6-inch thin-film lithium niobate wafer. This material is the key to the chip's power, boasting exceptional electro-optic properties that allow light to be guided and controlled with incredibly high efficiency. Monolithic integration. The chip carries over 1,000 optical components stacked onto a single piece of silicon. The term monolithic is the magic word that has stunned global researchers because everything is integrated. There's no need for external components, which minimizes signal loss and dramatically improves performance. The accelerator's function. This chip is not a universal quantum computer that can break encryption. Instead, it operates as an ultra-fast hybrid photonic accelerator. This accelerator leverages the key principle of parallelism unique to quantum computing, where massive amounts of information are transferred across multiple optical paths simultaneously. This gives it the super-speed advantage for specific AI workloads. The biggest obstacle to adopting quantum technology has always been scalability and manufacturing complexity. But the Chinese team has achieved unprecedented breakthroughs. Speed of deployment. While setting up giant quantum machines takes months, this chip is claimed to be ready for integration into a working environment in just 2 weeks. This shift places it, for the first time, among rapidly deployable industrial machines, not just laboratory models. Clustering. The chip is designed to be stackable and assembled with other chips, similar to clustering GPUs. When multiple units are linked, the system can behave as a gigantic network of quantum-inspired processors, with the promise of scaling up to 1 million photonic qubits. Mass production. The definitive proof of China's seriousness is the establishment of a pilot production line capable of producing about 12,000 wafers annually, resulting in hundreds of thousands of ready-to-use chips. This volume, while small compared to mega semiconductor fabs, is a pioneering step in the field of quantum photonics. Most importantly, they build a complete ecosystem: design, manufacturing, packaging, testing, and system integration, all done within a single environment. One of the precise engineering achievements that ensures this efficiency is the co-packaging design. Instead of separating the electronic and photonic components, they're placed side by side on the very same wafer. This extreme proximity dramatically reduces latency. Shorter distances mean much faster data transfer speeds. Noise and loss, reducing the path length, minimizes errors and signal degradation, which increases system stability. This intelligent mix of classic silicon technology and quantum photonic logic is what paves the way for the future of hybrid computing. What does this mean practically? For critical industries, companies in fields like drug simulation, biomedicine, ultra-fast financial forecasting, and aviation simulation can adopt this hardware without completely redesigning their data centers, because the chip doesn't require special cooling rooms. For the AI race, GPUs will not be the sole engine anymore. Instead, we'll see a future where photonic accelerators handle the massive computational tasks, while traditional electronic chips manage the low-power control and logic functions. Quantum computing is going through a historic moment, with different countries betting on different materials, like indium phosphide in Europe or lithium niobate in China. But this Chinese move confirms that technologies once considered a distant dream are now industrial products ready to change the face of the world. The race for the speed of light has just begun. Which application do you think will benefit the most from photonic computing speed? Share your thoughts in the comments, and are you ready for the age of computing by light?